You folks probably use the word entanglement tens of thousands of times a month, but for people who have not appreciated what entanglement means, like the fact that you took two of these things and you moved them far apart, and when looking at the state of one, you understand the state of the other. Um, how do you intuitively think of the word entanglement? In real life, like how should we think about two qubits being entangled? How does it even happen?
Yeah, I mean, so, first I'll say a non-accurate, like an inaccurate thing, but it'll help to explain, what the accurate thing is. So imagine that you're a person who always has their socks after the laundry well sorted, right? So you have socks that have many different colors, but always, your blue socks are with the blue socks, red socks are with the red socks, etc. Right? So now, if your friend sees your left leg has a blue sock, right, then he will be able to infer that your right leg also has the blue sock on, right? So this is what people mean when they say that, whenever you measure a set of entangled particles, right, if you see one, immediately know what the other one is as well. But where the analogy with the socks breaks down is because it's not because it's not that you wore a blue sock. It's almost like you wore a superposition. If you were wearing a superposition of a blue plus red sock, right? Even then, if your friend saw the blue sock, right before the measurement, there might be a superposition, right, of blue plus red. But as soon as one of them is measured in blue or red, the other one immediately collapses in blue or red as well, even if there's no contact between them anymore, right? So what that means is, right, you can have two qubits in a state of 0 0 plus 1 1, 0 0 and 1 1. And if you measure one of them in 0, the other one is in 0 as well. If you measure one of them in the 1 state, the other is in the 1 state as well, right? Now, sometimes, Einstein, I think, many people have kind of think that this means that you're violating the theory of relativity, right? That this is spooky action at a distance. It means that you are communicating faster than the speed of light, etc. But rigorously, you can show that that's not possible, essentially. But it is very non-classical, right? And I think a couple of years ago, the Nobel Prize in Physics was actually given for the experiments that tested, established that this property of entanglement.
Like one way that I try to think about it is parallel universes that we're basically
The
constantly
multiverse theory. Yeah.
we're constantly getting a sample of one of the parallel universes. And
You just made this simple last 1 hour into something a little bit more complicated. I thought it was a simple world that we were living in. Now we're living in a parallel universe. But keep going, because this podcast has no limits.
So, like, one way to think about it is that, so if let's say if I do a toss here and you do a toss there, and let's say there are many versions of this universe going in different universe, I get head, you get tail, you get head, I get tails, and so on and so forth. But and they're not correlated at all, but somehow an entanglement happens in every one of those universes. If I get a head, you get a tail, or something like that. And we don't understand why that happens, but
and what are the implications of that on a 100 qubit quantum computer, in the sense that we can now model things in unique ways? Like, what is the big deal with entanglement and computing?
Yeah. So there were two things, right? One is about the parallel universes, right? So that is like, it's again, we don't really know, right? And we don't have any way to test it, right? If there were parallel universes, how will you test it? Right now we don't have good ideas around that, right? Or maybe it is just that, like our notions around objectivity, that's just not that's not how things function, right? So we don't actually know. So there is but I hope that there will be some progress, and I hope that with quantum computers we will be able to perform certain kinds of experiments.
Sonika, I'm going to get into the realm of something really funny here, but when I was watching this entanglement video yesterday, it reminded me of my twin girls. I'm like, is it possible that they're entangled? Because they're identical twin girls. And I'm like, the more I watch the video, I'm like, is there something we said about entanglement between the two of them? And I don't want to take this discussion in that direction, but it's that sort of meta in my head right now. Like, what does it even mean to say that they're entangled?
I mean, the thing is that if at a quantum level, if two objects interact very closely with, how do you create entanglement, right? Like, I think you asked, how do you entangle two things? You just let them interact. If you write the equation, if two spins interact with each other for a certain amount of time, or two electrons or whatever, right? If two objects interact with each other for a certain amount of time, and then you take them apart, they are entangled, right? So entanglement is created through close interaction. So physically, like physics, from on the physics level, right? Like if two electrons are so close to each other that they have some Coulomb interaction, right? So the Coulomb, the Coulomb force emitted by one is affecting the other, right? Then they get entangled physically, right? And there are different mechanisms. So if they're electrons, maybe they're interacting through Coulomb interaction, right? If they're spins, they have some magnetic interaction, right? So there's some fundamental force.
Looks like their interaction changed their habits, and now when they're even far apart, they're habituated to that.
Yeah. So at a macroscopic level, we don't know quite how to describe this, right? We can write down what the equation for the interaction is if it's like small objects, but whether, and most theories of physics hold that at macroscopic levels we don't observe quantum effects anymore. But our knowledge of the universe is incomplete, right? We don't know really the fundamentals of even how do you measure a qubit? Even though we are building quantum computers, we don't quite understand them, right? So who knows how. I choose personally to keep an open mind about how quantum effects might emerge at macroscopic level, whether in our brain or a human society. But that's extremely speculative, right? I don't want to make any concrete statement about that.
But there was a part that talking about entanglement and these, let's say, 100 qubit computer. Like, how does it help computing?
The way it helps, the implication of that for large number of qubits is that it is only when you entangle something that you can get this exponentially large state space, right? So if you don't entangle them, then you will only have like you can describe it as you can describe each of the particles individually, right? They have their individual identities. Once you entangle them, then it's really like this many body, I call it a many body quantum state, where essentially each particle almost, you can say, does not have a unique identity anymore. It's part of this exponentially large state.
So I think in some ways, entanglement, the way you entangle them, reduces the state space to the interesting parts where sort of we're trying to do computation. Like, so if two electrons are entangled, not entangled, then the spin could be up, down, down here. If they're entangled, then essentially we're saying that if this is up, this has to be down. If this is down, then this has to be up, right? So in some ways, the entanglement reduced the number of possibilities from 4 to 2, but then that's what makes it also interesting.